Good morning, good afternoon, good evening. Welcome to our webinar on how to do an FMEDA using functional failure modes. Audio is provided via the GoToWebinar application. Make sure your audio is enabled in all the usual places. It's also available via telephone. Look at your invitation for details. There's a questions tool at the right side of your screen. Please use that to type any questions you may have. All of the attendees besides myself are muted. Onward. So my name is Rudy Chalupa. I've been doing this for a very long time. I'm designed everything from microphones to cable TV to industrial controllers. The last 2 decades or so, I've been working at Exida, and I've mostly been performing FMEDAs. So I don't like to call myself an expert, but I do like to think I'm experienced. Let's talk about Exida. Exida was founded in 2000 by some of the world's top reliability and safety experts, both from manufacturers and from certifying agencies. As it says, professionals around the world turn to Exida for help and guidance related to functional safety, alarm management, and cybersecurity. Among many other things, Exida offers 2 lines of engineering tools, actually more than that. But the 2 major ones are Excellentia, which is a suite of integrated engineering tools for end users, the people who use the products that you, the FMEDA analysts, are developing or your clients are developing. The other suite is OEMX, and we'll be talking a bit about that today. That's a suite of integrated engineering tools that provide a work process for OEM projects, people who are developing products. It consists of 3 modules: RecX for requirements generation, ArcX for doing FMEAs, and FMEDAX, which unsurprisingly is for doing FMEDAs. So let's get into it. What is an FMEDA? Well, it's failure modes, effects, and diagnostic analysis. What does that mean? Well, it's a bottom-up quantitative analysis to create failure rates for your product. Here we go, formal definition. A bottom-up inductive quantitative analysis where failure rates and failure modes of each component are used to predict failure rates and failure modes of an element. So you begin with a schematic, bill of materials, hopefully a list of diagnostics, and for each component, you look at the failure modes and assign them to the standard IEC 61508 output failure modes. It provides functional safety metrics. As you probably all know, there are 3 barriers to get SIL verification for a product. The first is systematic capability, which we really won't be discussing today. That covers the rigor of your design process, your manufacturing process, and your field return process. The other 2 are architectural constraints, which essentially show what degree of redundancy your product needs in order to meet a particular safety integrity level. There are 2 approaches to getting architectural constraints. The classic one, which is now called Route 1H, depends on a metric called safe failure fraction to determine the hardware fault tolerance or level of redundancy. that your product will need for a particular safety integrity level. The newer route is called Route 2H. And if your product has automatic diagnostics, as long as the diagnostic coverage is at least 60%, diagnostic coverage being dangerous detected failures over all detected failures, then there is a simplified approach that you can take to determine the required redundancy. Lastly, there's the probability of dangerous failures per hour, or average probability of failure on demand, depending on the demand rate. That provides the actual failure rates and also the operational parameters, useful life, and a proof test coverage. So here are all of the lambdas, which is failure rates that we need to fill in. In addition, there's useful life, proof test coverage, and diagnostic coverage. If you're designing your product via Route 1H, you'll need the top 4 of those: safe detected, safe undetected, dangerous detected, and dangerous undetected, to determine the safe failure fraction, which is the top 3 over all 4. That in turn, when you look at the tables in IEC 61508, will determine your hardware fault tolerance. For Route 2H, you'll first need to determine your diagnostic coverage, which I described earlier, and you'll also need to have a database which, as the standard says, has well-tried data. Then for the actual dangerous failure rate numbers, you'll need the dangerous and annunciation failures. In addition, you'll need to know your useful life and hopefully your proof test coverage. So the classic way of generating an FMEDA is what we call direct mapping. So you go straight from your component failure mode to the end product failure mode. So you'll need safe, dangerous, annunciation, no effect. It goes fairly well, or it used to 20 years ago. There are problems with it, though. If you need to change anything, you need to go back to all your components and figure out which components need to be changed and how they need to be changed. So that's the classic way of doing it, or as some of us at Exida would put it, the old way. So typically, as an FMEDA analyst, if you're not the actual designer, you'll receive a hardware schematic, bill of material, the specs on the components, or you'll need to go out on the net and get data sheets for those. But there are some things missing, like diagnostics and mitigations. So you start your way through the hardware schematic and you start entering components into your FMEDA, and you get to capacitor C19. And you say, okay, when this is shorted, the 5 volts goes to 0. What happens to the element when the 5 volts goes to 0? Well, if you can't figure it out, you're going to try to contact the designer. And okay, you call or email, and the designer is busy, and so gets back to you in a week and says, what capacitor was that? So you go back, since you've been doing something else for the last week or so, one hopes. You dig out the schematic, you try to remember where you were, you tell the designer it's C19, And then he starts looking into it, and you start talking about it, and eventually you get an answer. And then you go on your merry way until you run into the next component with a problem. Now, about a couple of decades ago, John Greavy here at Exida realized that if you added an abstraction layer between the component failure modes and the element level failure rates, that it actually made the analysis a lot easier. History lesson. So in the early 2000s, it really wasn't too terribly hard to do a direct FMEDA because there were only 4 categories in IEC 61508: safe and dangerous, either detected or undetected. It was a little more complicated than that because the different diagnostics had different levels of effectiveness, so you had to split stuff up between dangerous and not, dangerous detected and dangerous undetected, et cetera, but it wasn't too bad. Then, in order to do more accurate modeling at the element level, using the Excelentia tool, which internally uses Markov models, we realized that there were some failures which really weren't safe or dangerous. They were failures to the diagnostic circuitry itself. And so we added annunciation failures, annunciation detected, annunciation undetected. And then in 2010, things really got interesting. The second edition of IEC 61508 came out, and the definition of safe failure changed significantly. In the first edition, it used to be failure which does not have the potential to put the safety-related system in a hazardous or fail to function state. In other words, if it's not dangerous, it's safe. In the second edition, the definition changed to a failure that results in the spurious operation of the safety function to put the equipment under control into a safe state. In other words, a safe failure was no longer anything that was not dangerous. It was specifically those failures that caused a spurious trip. So now there were a whole group of failures which previously had been safe, but now were neither safe nor dangerous. For instance, let's say the LCD goes out on your transmitter, which is, up on a tower somewhere, so nobody can see it anyway. So Exida added a no effect failure category to cover those failures that were neither safe nor dangerous. So now there are a whole bunch of categories, and direct assignment is getting harder and harder. And it's also getting harder and harder to modify FMEDAs. In many cases, when you do an FMEDA, you'll discover that the product doesn't meet its intended safety integrity level, and the designer will make changes to the product. And it's basically, it's quite involved to go back through all the components and figure out, this used to be diagnosed at a low effectiveness, and now it's being diagnosed at a medium effectiveness. So you got to find all the components where that failure mode is part of their failure rates, and you've got to change your coverage from 60% to 90%. So putting the functional failure modes in between the component failure rates and the output failure rates, what you can do is you can divide your schematic up into subsystems, then figure out what the failure modes of each subsystem are, and then map the component failure modes to the subsystem failure modes. And then the subsystem failure modes are in turn mapped to the higher level. So this is the same as before, except instead of failure modes of an element, it says failure modes of a subsystem. And then the subsystem failure modes can be used to predict the failure rates and failure modes at higher level until you eventually get to the element level. So your failure modes at the component level go to a functional failure. For instance, if you have an input-output short, you would have this supply very high functional failure, which in turn would map to one or more of the output failure rates. Here's how it looks using the exida tool suite. So the FMEA is done in the ArcX module. So you have or create an architecture drawing, essentially a block diagram. You create, for each block diagram, you basically do an FMEA analysis. So a typical guide word analysis. Things are too high, too low, too fast, too slow, missing entirely, etc., etc. For each of those failures, you may have a mitigation, which could be an automatic diagnostic. It could be a proof or latent fault test. It could be something else. So, and then each of those diagnostics, you divide into the IEC 61508 failure mode. So safe, dangerous, enunciation, no effect, etc. When you get done with that, you've got your functional failure modes for each block. Then you go to the FMEDA and go through your components. And for each component failure mode, you enter the block failure mode, which lets the tool automatically sum up the results for the IEC 61508 required failure modes. So there are advantages to doing it this way. Ease of change is definitely one of the big ones. And as the example I gave earlier shows, going straight from the component failure rates to the element failure rates can be pretty involved. And unless you document it exhaustively, you may have trouble, and certainly somebody else may have trouble figuring out how you got from one to the other. You know, let's say you've got a power supply and you've got a feedback resistor, and the feedback resistor drifts high, and that results in a reduced output voltage. Okay, then you could say as the analyst, well, about half of that really is no effect, and the other half of it is dangerous, but we've got a low voltage detector and we'll give that low coverage, so that's 60%, but it's only on half the failure rate because of the no effect. So we've got 50% no effect, 30% dangerous undetected, no, 30% dangerous detected, excuse me, and 20% dangerous undetected. Okay, you come back in 6 months. It's going to be a bit of work to figure out what you did there. Another advantage is ease of comprehension, right? Because if somebody else comes and sees that 50%, 30%, 20%, they're really going to have to dig into it to figure out why the original analyst did that. And thirdly, ease of documentation, right? Because it's essentially self-documenting. You can say, okay, this resistor drifted low, and then you can see that the result of that is output voltage also drifted low. That's pretty easy to comprehend compared to 50% no effect, 30% dangerous detected, 20% dangerous undetected. Okay, so let's say I've convinced you that functional failures are the way to go. Well, next step is, how do you get the functional failure modes? So surely it should be available from a failure modes and effects analysis, right? Because that's what it is, right? You take your system, you divide it into blocks, you divide the blocks into blocks, maybe you divide those blocks into blocks, and eventually you get to subsystems where they're composed of components rather than blocks. And then for each of those blocks, you find problems, typically using keywords. Again, too high, too low, too fast, too slow, wrong input, wrong output, and then you're done. But a design failure modes and effects analysis means different things to different people. There are many ways of doing it. Different people emphasize different aspects of it. As an FMEDA analyst, you never know what you're going to get. So, for an FMEA, a design FMEA, the objectives are to find the problems and to recommend mitigations. So, for the FMEDA, we can use 4 pieces of information from the design FMEA. What the block is, what are the ways it can break, what happens at the next higher level when each of those failures occurs, and what mitigations are recommended or implemented. But we need more information than that. Sometimes the recommendations are just short descriptions. Sometimes the recommendations are automatic diagnostics. Sometimes they're proof or latent fault tests. We don't know how effective they are. So in that case, you're a lot further along, but you're not quite where you need to go. You have to go back to the designer, or you have to do it in a more rigorous way. So what else do we need? We need to know which of the recommendations are automatic diagnostics, if they are, how do they work? What's the diagnostic coverage, that is the effectiveness? What does the diagnostic do when it detects an internal failure? Obviously, a diagnostic that lights an LED on the PC board is going to be essentially useless compared to a diagnostic that puts an annunciation signal out or puts the device into its fail-safe state. Are there proof tests or latent fault tests that can detect the failure mode? Again, what is the effectiveness or coverage of that latent fault or proof test? So we could add columns to the spreadsheet to ask about these things. As FMEDA analysts, we could get rid of the columns we don't need and then add the columns that we do need. So now our design FMEA has turned into something that we at Exida call a design deviation and mitigation analysis. It's got the data we need and not the data we don't. So it performs the functions of the DFMEA that are essential for performing an FMEDA downstream, and also gathers the information needed to do a good functional failure FMEDA. Here's what it looks like in the tool. A bit of an eye chart, but bear with me. So let's say you've got a 5-volt power supply. In the tool, you lay down a unit called 5-volt power supply. And then in the tool, you can select Load Expert Knowledge, and you'll get this window. And if you've selected the unit to be a buck switching regulator, then the expert knowledge will come up with this set of deviations and multiple mitigations for a buck switching regulator. There are expert knowledge trees for many, many types of subsystem blocks. So you just choose which deviations you're going to consider, and for each of those deviations, you choose what mitigations you're going to consider. When you're done, you just click Load Subtree Requirements to the selected node, and presto, they show up underneath the unit in the tree view. For each deviation, you can click on it and you'll get a deviation node editor. This will already have the deviation name pre-filled. Add a description, add the potential effect, then you can assign it to the IEC 61508 categories: safe, dangerous, enunciation, no effect. If you click on this View Impact button, you'll get a list of all the types of failures, and you can divide up among them as you like. So in our previous example, you could say 50% no effect, 30% dangerous detected, 30% dangerous undetected, and you could give that a name. Then when you go to other deviations, if you click on the drop-down box, that name will be available in addition to the standard names. You also can enter your latent fault or proof test down here, if one is applicable, and the effectiveness or coverage for that. So for each deviation has one or more mitigations, which can just be there is no mitigation, or it can be a real mitigation. There you assign your level of effectiveness. If you just grab low, medium, or high, it will automatically assign the 60, 90, 99% numbers that IEC 61508 recommends. You can add a description of your mitigation, and then, of course, very important, you can say what action is taken if detected. Is it enunciated? Does it send the output to a particular state? Again, if the action taken is not in the drop-down list, you can type it in here and it will not only be used for this mitigation, it will get added to the drop-down list for other mitigations. It's also useful to look at the notes. The expert knowledge will add notes in here that typically are useful to determine if there are some of the usual gotchas involved in this particular mitigation. So you continue for each unit, each diagnostic, each mitigation, and then when you're done, your design expert deviation and mitigation analysis is done as well. At that point, all that's left is to add all the components, map the component failure rates to the functional failure rates, and then the FMEDA is done. In conclusion, generally, you think it's a bad idea to add more work, but in reality, it turns out that if we add these functional failures in between the components and the element, the overall amount of work that's done is actually less, and the documentation is improved immensely. And that's the end. If you have any questions, please enter them into the question tool at the right side of the screen. If you'd rather read a white paper than play this webinar back, there's a white paper on functional effects at this address. If you want a demo of the OEMX tool, just email academy@exida.com and someone will get back to you arranged for a demo. While you people are busy entering lots and lots of questions, I think I'll point out some of the educational tools that are available from Exida Academy. So there's online self-paced training, in which case you get access to a course for 60 days and you can learn at your own pace. I'll point out for designers in particular, FSE 211, 212, and 213 are functional safety for design and development, software design and development, and mechanical design and development. Also worth pointing out is OT 214, which is application of ISO 26262 to semiconductors. This is for FPGA systems on chip, larger semiconductors. How do you apply ISO 26262 to those? Also, there's going to be live training in the next few months. We'll particularly look at the Certified Functional Safety Practitioner exam preparation workshop, which will be in person in Sellersville. You can find us at all the usual social media. Here is my address and how to reach us. All right, let's take a look at the questions. All right, Anand asked, why is ISO 26262 not mentioned? Well, so ISO 26262 is a derivative standard off of IEC 61508. As you probably know, 61508 is sort of an umbrella standard, and then there are sector-specific standards. So ISO 26262 for automotive, 62061 for machinery, 61511 for the process industry, et cetera, et cetera. So I'm mentioning 61508 because it's the umbrella standard, and the things that we look at in 61508 will trickle down to those other standards. The one other question I see here is, how can you calculate diagnostic coverage? Well, diagnostic coverage is actually given for a lot of diagnostics in IEC 61508 itself. And so that pertains to all the derivative standards as well. If you look at Annex A and Annex B of 61508-2 and look at IEC 61508-7, that will typically give you the diagnostic coverages for a particular type of diagnostic. And that covers all the questions. Thank you very much for attending. Enjoy the rest of your day.